Hello everybody, today we will be going through the lab number 4 and recitation number 6, flow through a Venturi and discharge through an orifice. We will start with the flow through a Venturi. So a Venturi meter determines flow rate like the wires. The good thing about this instrument is that it has a very small head loss, and it is very suitable for many applications like in metering and mixing devices. It also eliminates any jet contractions. The picture shows the arrangement of the Venturi meter. We have water enters through a flexible hose to the meter, so our flow rate will be entering the system in this direction. A control valve downstream controls the flow, so we have here a control valve for the instrument in which it can control any flow rate. So if we have a flow rate Q1, it can create a different flow rate Q2, and it can increase or decrease the pressure for the instrument. And after the valve, the hose leads to the hydraulic bench. So when the water goes out of the system of the instrument, it will go to the hydraulic bench and recirculate, just like the last experiment. There are 11 tubes connected to pressure tappings along the Venturi wall. As you can see here, we have 11 tubes connected to the Venturi wall, in which each tube will have a letter. So we have from letter A to letter L. Each letter has a different specifications and a different diameter, area, and distance from the datum. So each cross-section area will be different to analyze the changes in pressure. Those tubes are connected to the manometer tubes. So these tubes are connected to the manometer tubes, which are these, and at the top end to a common manifold with a small air valve. So there is a common air valve in here in which all these tubes will be connected. So the system will be one. You can see here that the letter A is the start of the system with its own cross-section area, and the letter D is where the contraction occurs. So we will be analyzing the letter A and the letter D later on to determine the coefficient of discharge and the changes in pressure from all the points, or the letters in this case. So a little bit of theory. Consider the flow of an incompressible fluid through the Venturi tube shown in this figure. We have the direction of the flow, as I stated earlier. The cross-sectional area at the upstream section 1 is A1 in here, and at any other arbitrary section, in which case will be A2, A3, A3, and so on. The piezometer tubes at these sections register levels of H1, H2, and Hn. So we can see here that at this level, the piezometer tube register a pressure head of H1, and here of H2 and Hn, and so on. We can see here that under A1 we have a pressure head H1, and under A2 we have a pressure head H2. This tells us that the more area, the more pressure. So we can see here, we can clearly see that our cross-section area A1 is bigger than our cross-section area A2. So here there's a contraction. The more the cross-section area, the more pressure head we have. Similarly, the more velocity the cross-section area has, the less pressure it generates. So we can see here that we have the same flow rate, and the velocity under A sub 1 will be smaller than the velocity under A sub 2, because it's a bigger cross-section area, it's therefore a smaller velocity. So the more the velocity a cross-section area has, the less the pressure. We will analyze how this works in the discussion part later on, but it is interesting to see how the more the velocity, the less the pressure it generates. So for this experiment also we will also find our Q, and we will find each one of our H under the different letters discussed before in order to find our coefficients. So in order to find the coefficient of discharge, after we obtain the experimental Q and the H sub n plot, and the H sub n, we have to plot the square root of H1 minus H2 against the flow rate. So H1 and H2, and the way we are going to analyze this is that H1 will be the start of the system, will be 1, and H2 will be where the contraction occurs, so in this case will be D. So here's A1 and 2, so it will be A1 and D2. The coefficient of discharge C is the inverse gradient of the line. So after we find all our flow rates and all our square roots of H1 minus H2, we will build our plot, and then we will find our gradient, which is the slope, and therefore the coefficient of discharge is the inverse of the gradient. So our gradient will be the inverse of the slope, to put it that way. Also, we can find the C can be obtained by this equation. So for the results and the data, the ideal or theoretical dimensionless pressure difference is given from the area ratios. So we will have our ideal dimensional pressure will be A sub 2 divided by A sub 1 to the power of 2 minus A sub 2 divided by A sub n to the power of 2. And in order how to calculate this value, we will have our table of the experiment data, in which we have our piezometer tube. You can see here that there is each letter A, B, C, D, E, F, G, H through L. We can see here, as I explained before, that we will analyze A and D. So under A and D there are the numbers 1 and 2. So we have also our diameter of each cross-section area and our area in millimeters square, in square millimeters. So in order to find our A2 divided by A sub n, for the first row we will do and get this value 201.1 divided by 530.9. And for the second row it will be 422.7. I'm sorry, it will be 201.1 divided by 422.7. So the letter N basically means is the row that we are working on. So for this column we will always start with 201.1 and then divided by the row we are in. So basically that is how we fill these tables, and then we can find our ideal and the ideal dimensional pressure. So for the actual or experimental dimensionless pressure difference are found from this equation you can see in here, and with when an ideal flow and Bernoulli's equation, we can have the velocity in the part 2, which gives us this equation. We have all the data to find the velocity at the point 2, and also and we have to fill the table 2.4, and we have to take our H sub n and H sub 1 in the handouts or in the experimental data sets. So we have the same here as the table 2.3. We have the piezometer tube, the letters A through L. We have the diameter of each cross-section area. We have the pressure head, which is exactly what we are getting from the manometer. There is a picture here. We can see here that each pressure head will be in this case this water level, for A, this water level for B, this water level for C, this one for D, and so on. You can see here that we will be analyzing A, which is number 1, and D, which is number 2. And you can see that the pressure level at D, which is the contraction, it's the lowest of all of them. We can see that the other pressure levels are in this direction. And we can see that when we have the smaller the cross-section area, the smaller the pressure we have. And then we find our pressure head, and we do the same H sub n minus H sub 1. We do exactly the same as the first table in order to find our actual dimensionless pressure. Remember that we can calculate the velocity at the section number 2 because we have all this data. And then we need to compare these two columns. And we don't need to build any kind of plot for the pressures. We can just compare every row with each row to see if there is any big variance between the two of them, and we can like discuss it why later in the discussion part. So here, as I said, we are comparing the pressure between the ideal pressure and the actual pressure. But right now we are going to obtain the coefficient of discharge. So in order to do that, we will need to do 6 trials. We will need to do 6 trials with different flow rates, and we will need to obtain the A1 and D2, which is H1 and H2. So we can see here that we will obtain our flow rate the same way that we obtain it in our lab report, in which we will use the hydraulic bench. We will have a mass of water in kilograms, we will have a time in seconds, and then we will need to obtain or record the H1 or H2 under that flow rate. So we will have different H1s and different H2s. We can also obtain the flow rate. We will do H1 minus H2, and then we will do the square root of H1 minus H2. So this square root of H1 minus H2 is exactly what we are plotting here. So if we plot the square root of H1 minus H2 against the flow rate, we will obtain a slope. I am going to move this graph a little bit to explain the slope. Okay, so the plot should be a straight line, a regression through the origin, provided the value of C is constant over the range. Sorry. So we have our plot. So imagine we have our data like this, and we will produce a regression line. So this regression line, it has to go through the origin. So it has to start through the origin. So in the regression analysis, when you do an Excel, don't forget to put that to obtain our regression line and equation going through the origin. So we will have a equation more or less like this, where M will be our slope, and then we can write this as the square root of H1 minus H2 equals to K, which is our inverse gradient multiplied by our flow rate. Then we would have that our K is equals to the square root of H1 minus H2 divided by our flow rate. And then, since it says that the coefficient of discharge C is the inverse gradient, we will need to do the inverse gradient equals to Q, the flow rate, divided by the square root of H1 minus H2. So this is the this is the value you will need to this is the value you will need to obtain from our regression line. So you obtain a whatever m in here, so you will need to convert into this way, and note that it is exactly the same way that as this is C equation. And then our final C equation will be 1 divided by a2 the big square root to g1 minus a2 divided by a1 to the power of 2 multiplied by 1 divided by k. So you will have to find these. So you will obtain this, and you will find a coefficient of discharge based on the plot. Note that you can find an individual coefficient of discharge in this column, because we will have our own flow rate and our own H's, and our own H and our own areas of the orifices. We have everything in here, but the most important thing is to find our coefficient of discharge C based on the plot, because that will be our average one, and that is the one that we will be analyzing. And then also we can also create an average in C, but it is not going to be the same as the average from the plot. So so in order to complete the discussion, we will need to obtain the C from the plot. Some things to help out is that to calculate the experimental flow rate Q, we use the mass of the water that you have from your experiment and the equation of the density, mass divided by volume, to find the volume, and then divided it to the recorded time. Like I said, is exactly the same way as the last lab report. The volume flow units equals 1 cubic meter per second equals to 1,000 liters per second, and equals to 1,000 kilograms per second, assuming that the 1 kilogram assuming a density of 1 kilogram per liter. The flow velocity will be equals to mu equals to q divided by a, and all the units must be on a metric system. For example, so for the velocity at the throat, divide the q with the area given in A2, which is the throat. Remember that the sub 2 is always considered in the contraction. Also, we have to be very careful in what units are given in the tables. So for the discussion part, this actually is going to be very important. We can also talk about the ways how to improve the device. For example, we can see that the device is having leakages. We can see that our results show us less pressure than the ideal, so it could be some losses of pressure in the device or some leakage. Also, our time judgment, the flow rate calculation is very important, so it could be errors in human errors, and also human errors in the time. So that is some ways how to improve the device. We also did this the last report, so it will be very similar. And also the number 2 is going to be required to do in the discussion part. It is an independent question, but it is a question following all what we learned right now. So we have to use an average value C for the experiment. This average value of C is the one and only C value that we will obtain from the plot. So remember to plot this is very important. Remember the units that are given. So we will use the average value C for the experiments to determine the throat diameter of a Venturi meter, which will measure the flow of 0.4 cubic meters per second in a pipe of 0.6 diameter with a differential head of 0.8 meters. This differential head will be h1 minus h2. So we will have all these parameters with the average value C that we already obtained, because that was actually the most difficult part of this experiment, because we need to find what is the C of our instrument. So once we got the C, we can resolve any kind of problem. So make sure that to add this problem to the discussion section with the answer. So right now we will go to the second part of the experiment, and we will discuss the discharge through an orifice. An orifice is a simple and cheap way to measure a flow rate. It can work as a flow regulator because they develop a substantial head loss. So remember that the Venturi meter, one of the pros of that instrument is that it has a very small head loss, but this one is also could be as a pro that it has a substantial head loss, because it could work as a flow regulator. When a fluid passes through an orifice, the fluid stream contracts. The contractions reduces the overall flow. So if we have a flow rate going in this direction to a pipe, and then we have a contraction, all the fluid will generate a smaller flow rate than the one we had here, and then we have a head loss. Then we would have a head loss. The equipment that we will be using, it's basically a transparent cylindrical tank held between a top and a bottom plate. A water inlet on the top. So here, as usual, we will connect our hose from the hydraulic bench, and the flow rate will go in this direction, in which it will fill up the tank. An overflow pipe, which is this one. An outlet hole in the middle of the bottom of the plate, in which we will analyze the discharge through the orifice. The orifice that fits into the hole in the bottom of the tank. So this orifice, or this discharge, we will go back to the hydraulic bench, recirculating the system, as we discussed in the past weeks. We have also a manometer to do our measurements, and a pitot tube and a micrometer. So the pitot tube and a micrometer, it will measure the head loss in the discharge of the orifice. How it works? So water enters at the top of the apparatus through a vertical inlet pipe. As I just said it, the water will enter here from the hydraulic bench. The bottom of the inlet pipe has a water settler which sits below the normal water level and helps to stabilize the flow that enters the tank. So here is our water settler, that it really helps settling the flow, because what we need when we need here, when measure the head of the apparatus, is to have a very stable flow in here. The overflow pipe directs the surplus of drain and helps to keep the water level constant. So for example, if we have a flow rate Q1 and it's bigger than our discharge Q2, if Q1 is bigger than Q2, the system will fill up and then it will collapse. But that is why we need the overflow pipe. So the water level will never be higher than this. So since you can see here is the overflow pipe. The overflow pipe. The rest of the water passes out through the orifice fitted in the bottom of the tank. So we have water going into the hydraulic bench through the overflow tank, and water going to the hydraulic bench through the orifice. The jet passes over the pitot tube, which measures the total jet head, and back in the hydraulic bench. So the pitot tube will be measuring the total jet head. Remember this, because this is one of the values that we will be calculating. The pitot tube assembly includes a micrometer, which allows you to accurately measure the width of the jet. So in this case, the micrometer is a very accurate instrument in which we will measure in the order of 0.1 millimeter the diameter of the jet. 1 manometer tube fitted at the bottom of the tank show the water level in the tank. So we have two tubes in the manometer. One will be to measure the water level in the tank exactly here, and the other tube of the manometer will be to measure the total jet head. We have here a little bit more close-up of the of the pitot tube, of the pitot tip and pointer. So here we will be measure the jet head. We can see here that the flow, we will have a flow going in this direction. We can see here like clearly contraction from the whole tank, and just giving this space to generate a flow rate. And remember the last lab session, the velocity measurements. This is exactly the same. This is exactly the same way how we measure the velocity and the pressure head in the other manometer. Here it has a frontal orifice, and it will calculate, or it will get the pressure, and we will obtain as a jet pressure head. So as we can see here in this picture, the pitot tip will move in this direction to the right and to the left in order to obtain the the diameter of the orifice. So this actual pitot tip does two things. It will obtain the jet head, and also will obtain the diameter of the jet, or of the jet. So for this experiment, two nozzles will be examined: the standard sharp-edged orifice and the angled entrance and exit orifice. We can see that each nozzle will have a different configuration, and therefore it will have a different discharge coefficient, just like we just calculated for the Venturi. These ones also, it will have their own head loss. So as you can see here, for the standard sharp-edged orifice, we will have our orifice, our flow going, and the cross-section area will increase to a different cross-section area, and it will generate our jet flow. And at the same time, another configuration is to contract the cross-section area just at the middle, and opening, closing, and opening, and going through the flow. So these two will generate a different head loss. It could be more or less than the regular ones. In the first part, water is admitted to fill to height of the overflown pipe. This ensures that the level remains constant. So that means that we have to let the instrument to fill almost completely, or let the overflow pipe to work. Then discharge is obtained to the hydraulic bench Q. We will obtain our Q the same way we have been getting it through the hydraulic bench. We will have a time and a known weight, and H sub 0 through the manometer attached to the apparatus. So H sub 0 is the water level of the outer cylinder of the apparatus. So H sub 0 is the Q, and H sub 0 are the parameters we will need to obtain in the experiment. And also, to measure values of the stagnation head H sub C, the stagnation tube is inserted into the emerging jet close to the underside of the apparatus. So this is exactly what we are going to obtain the stagnation head, or the jet head. We are going to put the pitot tip into the jet flow, and to obtain an HC. So this is also the other parameter we are going to obtain. And finally, it is necessary to find the diameter of the jet. So with the micrometer, we will find the diameter of the jet, or the diameter of the flow rate after it comes out from the nozzle. A little bit of theory about about the flow through the orifice and nozzles. So the drawing A shows fluid streaming through a smoothly contracting nozzle, this making a parallel jet. So we can see here that this nozzle is rather smooth rather than the ones we are going to analyze. You can see that they are very stiff, and it has a very harsh edges. So we have in the case of A, we have a very smooth contracting nozzle. The overall increase in speed through the contraction reduces non-uniformity in the flow. So we will have a uniformity in the flow. The fluid velocity is uniform across the emerging jet. We can see here that that just at the finishing of the nozzle, we will have the same diameter in the jet. There is no contraction. In drawings B and C, the fluid doesn't emerge as convergent stream, so the cross-section area of the jet reduces to a contracted section or vena contracta. In this section, streamlines parallel and velocity is uniform. So we can see here in case B and C that since we have a very harsh nozzle or a very hard nozzle, a contraction will be generated. We have just at the moment it goes out from the nozzle, we will have one area, cross-section area, and then we will have a second cross-section area or a smaller one before getting a uniform flow. In the same here, we have another nozzle with a higher head loss. We can have that there is a more pronunciated contraction before getting a uniform flow. So the theoretical cross-section area showing the main features of this experiment is that we will need the area sub-zero, which is the area of the orifice. This data is given in the experiment. We will obtain with the micrometer the area the contracted area A sub C. We will obtain our H sub C and our H sub O from the manometer as discussed before. The previous graph shows the cross-section area of the tank. We have to have some assumptions here because even though we are considering the head loss of the nozzle, we have to consider these assumptions. We have to assume that the tank is large enough that there is no fluid flow except for the part near to the orifice. At the orifice, the fluid accelerates towards the center of the orifice. The curvature of the streamlines shown as Mn reduces the jet diameter. So we can see here at the point M where there is no contraction, and at the point N it produces a contraction of the flow. The reduction in area due to the curvature extends to a downstream position at a distance between half orifice diameter and a complete diameter. So these are the assumptions we will need to consider in order to do the experiments. It's going to be very good to put this in the background theory. So these are the total head of water at points M and N. M will be at the cylinder or at the system, and N would be when the contraction occurs when the water goes out to the system from the system. Here is N, and M is just at the system when there is no contraction. Then we have the total heads. So energy is conserved. For example, if there is no loss of total head, we will have the Bernoulli's equation. Pn and Pm are atmospheric pressures, and U sub m is negligibly small according to our assumptions. So we are considering that U sub m is the velocity in our system, and we can consider that it's 0 because we are not analyzing at that spot. Also, from the diagram at figure 13, you can see that Zm minus Zn equals to H sub 0. We can also assume that Zm minus Zn equals to H sub 0. So from the above equation we get that H sub 0 equals to mu sub n to the power of 2 divided by 2 gravities. These results applies to all the points in the plane of the vena contracta, so changing the notation to let u sub 0 be the ideal velocity in the plane of the vena contracta, which would occur if there was no energy loss. So our H sub 0 will be our mu sub 0 to power of 2 divided by 2 gravities. Yeah, so remember this equation will be if we don't have any kind of energy loss, or if we consider as an ideal flow. So because of the energy loss, which in fact takes place as the water passes down the tank and through the orifice, we can see that there is a contraction, obviously, because of the nozzles. The actual velocity mu sub c will be our actual velocity, not our theoretical, in the plane of the vena contracta is less than mu sub 0, because mu sub 0 is our ideal, and mu sub c, putting all our head loss, will be smaller and might be calculated from the pitot tube using the following equation. So H sub c will be equals to mu sub c to the power of 2 divided by 2g, with the energy loss being equal to H sub 0 minus H sub c. So this is the tables that we will use for our experiment. We will have, and we will do 5 trials with different flow rates. We can see here the trials. Again, we will use the flow rate, we will calculate the flow rate through the hydraulic bench. We will have our mass of water, we will have our time, and then we will obtain, for each flow rate, we will obtain a H sub 0 and H sub c, which the H sub 0 is the water level at the apparatus, and the H sub c is the stagnation head, the pitot tube at the edge of the water jet. But then we will obtain the width of the vena contracta using the micrometer. This data we will have, and then you will need to calculate our flow rate, and then we can put in also in the table H sub 0 to the power square root of H sub 0 in order to obtain our coefficients Cu, Cc, and Cd. The same thing from the orifice number B. Remember, we will, for this experiment, we will use 2 orifices, the sharp edged and the angle one. So we will do this thing 2 times. So how to calculate Cu, Cc, and Cd? The coefficient of velocity Cu is the ratio of actual velocity mu sub c and ideal velocity mu sub o. So the C sub u will be equals to mu sub c divided by mu sub o. Or it could be defined as the square root of H sub c divided by H sub o. So the Cu is pretty straightforward. We can calculate with the data we obtained in this table. The same way with the coefficient of contraction Cc, the ratio of the cross-section of the vena contracta AC to the cross-section area of the orifice AO. So the C sub C equals to the A sub C divided by A sub O. The A sub O is a data given, and the A sub C is the data obtained in the experiment. With a micrometer. So finally, the coefficient of discharge CD is the ratio of the actual discharge to which would take place if the jet discharged at the ideal velocity without any reduction of area. So we have that the actual flow rate equals to the mu sub c multiplied by A sub c, and the ideal flow rate, it will be Q sub O equals to mu sub O multiplied by A sub O equals to A sub O the square root of 2G H sub O, being A sub O the orifice area as we discussed before. And then we will obtain the equation of CD, which is Q divided by A sub O multiplied by the square root of 2G multiplied by H sub O. If we rearrange the previous equation of CD, we would have CD equals to 1 over A sub O multiplied by the square root of 2G multiplied by Q divided by the square root of H sub O. So if we set that K equals to Q divided by the square root of H sub O, and then if we plot our flow, in which we have our flow in here. If we plot our flow, and then we will plot our head, our square root of head, in which we also have, and that's why it's very helpful to do this column, H sub 0 to the square root of H sub 0. Then we will obtain the K, which will be equals to Q divided by the square root of H sub 0. So our K or our slope in our linear regression equation. So for example, we have our points like these, and we will create our regression line, in which we will have a regression line equation, and then this M we can be equals to this, and we put it in here, and the same way like as the Venturi part, we will obtain our mean CD. So just saying again, from the slope of a chart of Q against H against the square root of H, you can find K, which you can use to find a mean value of CD. As I said, we can also find our own CD for each one of the trials, but the best way to do it, and the way to do it, is we have to find the CD from the plot, because that is the average of all our experiments. Finally, between the three coefficients, the following relation exists, that the CD equals to CU multiplied by CC. So this is also important to compare it later in the discussion part. So for the discussion part, or the discussion results, don't do the questions for discussions asked in the manual. Actually, these equations for this manual, they are different, and they vary from year to year. And also for the discussion part, I just asked to do one specific question. I think in the lab manual for the Venturi there are more discussions, so just do the questions I am asking you in this video. So we have to compare all the C sub U and the C sub C's and the C sub D's we obtain. We can compare them with the typical values of their circular sharp-edged orifices given by the manufacturer, which are these. So for the C sub U and the C sub C, you can do the average obtained in each trial, but for the C sub D, you must do it with the plot. So then you can compare them with this manufacturer data given, and you can also check your work if CD equals to C sub U multiplied by C sub C. And also furthermore, we can also check that we can say that a reasonable estimates of maximum errors are these. For CD is plus minus 2.1%, for CU is plus minus 1%, and for C sub C is plus minus 1.8%. So you have all these data given, and you can compare all this data to all the experiment data you will calculate in order to do the discussion. As before, things to help out. To calculate the experimental flow rate, you use the mass of water that you have from your experiment and the equation of density to find the volume, and then divide it by the recorded time. Also remember that the volume flow units, and be very careful with the units given in the tables, because sometimes, for example, the tables have the units of Q, or you will need to build the plots with the units of Q to the power of 4. So remember that to plot in this format in order to obtain good values of CDs. So I guess a little bit this lab report is a little bit complicated or a little bit complex, so be careful also to analyze your CDs correctly. Don't mix out the two tables, even though they are quite similar. And if you have any questions, please let me know, or if you have any suggestions or of how should I do the videos, I I would appreciate some feedback, and let me know or email me, or we can arrange a Zoom meeting if you have some questions about this lab report. Thank you.